So up until now, all of you have seen only algorithms in this course. And the agenda for today is, and for the rest of couple of more lectures, is to build some hardness. For parameterized problem. Okay, so let's start from the NP completeness reduction, which we all know, or the many one reduction. So how do you show a problem to be NP complete? So you have a problem A, and say basically you give an algorithm that, given an instance x of A, outputs an instance y of B with what property? Such that x is in A if and only if y is in B, or x is a yes instance of A if and only if y is a yes instance of B. Okay, so this is what we have seen in NP completeness reduction, that given a problem A, we give a reduction to problem B, which just means that you give an algorithm that takes an instance of A and outputs an equivalent instance of B. And what do I mean by equivalence? Equivalence means this. This is what means equivalence. Is that if I start with a yes instance, I give you a yes instance, and if I start with a no instance, I give you a no instance. So in other words, suppose here are sigma star, okay, and here are yes instance of A, and here are no instance of A. Then this algorithm, and here is the yes instance of B and no instance of B. Okay, and then what do these take? So if you have given me instance here, this guy will map somewhere here. If you have given me an instance here, it goes and maps here. It's not that given an instance here, I map it here. This does not happen. Okay, and how much time does this algorithm is allowed to take? Because what do we want to achieve by this reduction? We want to say that, look, in NP hardness reduction, that look, if you had a polynomial time algorithm for B, then I can design a polynomial time algorithm for A, right? So if B had a polynomial time algorithm, then we can design a polynomial time algorithm, for A. And how will that algorithm will look like? Basically, that algorithm is going to do like this. So here it is algo for B. What I will do, given an instance of X and instance of B, I will feed him, I will run my polynomial time algorithm here. Let's call this algorithm curly C, okay. Run curly C on X and obtain Y, an instance of B. So what I do now to this algorithm, what I'm going to do, I'm going to feed Y. and now this is going to give me yes or no answer because I have an algorithm for B. Now what does this tells us? If X is a yes instance, if and only if Y is a yes instance. So now if I wanted to test whether X is a yes instance or not, I transform into Y, I run an algorithm for B, right? And if it says yes, I return the same. I say yes, X is yes or no accordingly, right? So that is the whole objective, right? So what is the whole objective? And since this algorithm we have assumed to be polynomial time and we want whole algorithm to run in polynomial time, it is imperative on us that this algorithm C also runs in polynomial time, right? So this is the whole, this is what you do when you're trying to design a many to one reduction to show a problem to be NP hard or NP complete. Let's fix the word NP hardness because NP completeness I do not want to go into. So this is what you do. Now I would like to have an analogous notion first of reduction for problems to show that it is not fixed parameter tractable, right? Now there are two things to understand, right? One, how much I'm allowed to take time, and how the instances can be modified, right? These are the two things which we have to take care of. But now let's ask ourselves, what is our goal, right? What is the goal we are asking here? In, like for example, what we would like to say, look, if we had a fixed parameter tractable algorithm for B, then we will be able to design a fixed parameter tractable algorithm for A, right? And in FPT world, an instance of A is going to be tuple. What is this instance of A? It's going to be tuple x comma k, which is an element of sigma star plus natural number, and B is also going to be some y comma k prime element of sigma star cross natural number, right? Now we have to ask ourselves, what are we trying to achieve? So suppose I have x comma k, right? And suppose this algorithm for B, I mean it's an FPT algorithm, so given some parameter k and input of size n, suppose it runs in time tau k. So if you give him an instance, y comma say k star, it runs in time tau k star times mod y times c. Suppose this runs in this much time. Now what we would like to do, we would like to have an algorithm which takes an instance x comma k of A, outputs an instance. So now what we like to have is, given an instance x comma k of outputs an instance y star, let's say y k star or say k tilde of B, okay. Now so okay fine, we obtain y tilde, y k tilde, and I would like to run y k tilde on this much running time, okay. But now let's try to understand some simple things. So first of all, what is my objective? Whole thing should run in running time how much? If I am trying to design a fixed parameter tractable algorithm, for what? For a problem, for an instances in A, right? So I want to design a fixed parameter tractable algorithm for A. So given an x comma k, again let's write down x comma k, an instance of, it should be A, okay. Given an x comma k, an instance of A, what is the final running time? I want to be some f of k times mod x, some alpha where f is some function depending on k alone and d is some fixed constant. Right? Like, so not d, what is this? Alpha is some fixed constant. So alpha is like 10, 20, 30, but it is fixed. Alpha could be anything. I mean, maybe 10 to the power 10, but it is fixed. Okay. So this is my goal. Now, if this is my goal for some f, how much time can I allow this subroutine to take? and I still will be okay. How much time does C can take and we still will be okay, right? When we were doing polynomial time many to one reduction, we allowed ourselves to be polynomial here. But now all I want to rule out is such an algorithm, right? All I want to rule out is such an algorithm, right? F of k mod x to the power alpha. This is what I want to rule out. It means I can take that much time to construct this instance y k tilde. So in any complexity theory, if you're trying to give a reduction and you're trying to rule out certain kind of running time, then you can actually take that form of the running time or that amount of running time to construct those kind of instances, right? So it means this algorithm could be a fixed parameter tractable algorithm. So this transformation from A to B, given an instance x comma k, I can take fixed parameter tractable amount of time and produce an instance, equivalent instance y k tilde. Okay. So first is outputs an instance given an algorithm. So how much C is allowed to take? So let's see this C. Now I relax myself from polynomial. I say, hey, doesn't matter, you can take any h of k n to the power say alpha 1, where alpha 1 is a fixed constant. So you're allowed to take that much amount of time, okay? And what do I would want to do? I would like to do, given this y and k tilde, run this algorithm. So now what will the running time of my algorithm, total running time of this algorithm will be? Let's write down. Now I given x comma k, okay, I took time h k say mod x to the power alpha 1 plus now I am running this algorithm on this instance y k tilde. So how much time I am going to take? Well, I am going to take time, let's see how much time I can take. I can take time if it is runs in tau k tilde times mod y times some c, right? This is the running time will be, right? Because I first obtain an instance y k tilde, then I run algorithm on B, right? I run algorithm B on this instance and I check whether this returns yes or no. If it returns yes, I say that my given instance is yes. If it returns no, I say that it's a no instance. Now let's do one reduction. What is the first favorite reduction we do in the course? Okay, this is a very simple. So do you know a reduction from independent set to vertex cover? Do you know a polynomial time meaning one reduction from independent set to vertex cover? Yes. No. So what is the instant? Like, if I give you a g comma k, it means whether instance of independent set. What is an instance for vertex cover? This is an instance of independent set, right? What does my algorithm tells me? That in polynomial time you should output me an instance of a vertex cover in such a way that this is an yes instance if and only if the other is an yes instance. So now you tell me an algorithm which will given an instance of vertex cover gives me or outputs me an instance of vertex cover. Manus? Right. So my algorithm does nothing, it just changes k to n minus k, right? Now all of you know that if G has a vertex cover of size, G has a vertex cover of size at most k if and only if G has an independent set of size at least n minus k. So this is a valid reduction. If I have a vertex cover of size at most k, then its complement is an independent set and I'm happy. If I have an independent set of size at least n minus k, then I know that its complement is a vertex cover, so I'm also happy here. Okay. Clearly, this reduction took time, FPT time, like some h of k n of alpha, where h of k is an identity function. It just took a polynomial time, because all we did is given an instance, we return this. So clearly this is an FPT reduction. So any polynomial time reduction is also an FPT reduction, right, with respect to the running time. Okay. Now if this is a reduction happened, right, now what is the problem? What is the problem B? Is a vertex cover. Tell me what is the fastest algorithm you have seen in this course for vertex cover? Algorithm for vertex cover. I mean, it's not a black box, you know an algorithm for this. Tell me an algorithm which you have seen for the vertex cover with some running time. Great. 1.618 to the power k time n square, n cube, n 100. Sure, n 100 works for me. I mean, I'm sure you can do it n to the power 100. Now what happens? Now we are set. We gave a reduction. It took an FPT amount of time. In fact, it took polynomial amount of time. Now I would like to solve independent set using this reduction. Now let's see what happens. So for this reduction, how much running time did I take? I take some n to the power big O of 1 for the reduction, so it's polynomial. But now how much I'm going to take here? 1.618. What is my k tilde? K tilde times n to the power 100. I can solve this and I will be happy. But is this an FPT algorithm? Why? Because look at k tilde. K tilde is n minus k, right? K tilde is n minus k. So all I have got is basically an algorithm with running time 1.618 divided by 1.618 to the power k. By no stretch of imagination, I can say that this is an FPT algorithm, right? For an FPT algorithm, we were supposed to design an algorithm which ran in time f of k times polynomial in alpha, where k was the input parameter. So now not any reduction is okay for me. So what kind of reduction is okay for me? Like what kind of reduction I can allow and what kind of reduction I cannot allow. Like, because this reduction does not work for me. Okay, let's look at another reduction. Okay, let's see if this reduction is fine with me. Clique. So what will the reduction from independent set to clique, polynomial time any one reduction? No one there?
Keeping the parameters same, we just make the graph is complement of original graph and the parameters.
Good. So all I do is take the complement and this, right? Now clearly G has a independent set of size at least k if and only if G bar has a clique of size at least k. Now what happens if I try to do this, right? Well, now if we had such an algorithm for the clique, if we had an algorithm for clique which ran in this much time, then we are happy because it's no more n, it's just k, because k tilde and where k tilde is k. So this is a parameterized reduction, right? Because if I had a good algorithm, FPT algorithm for clique, then combined with this reduction, it would imply that we have got an FPT algorithm for independent set problem. So what is a motivation? What is this? I mean, what would have changed if somehow it would not have been k here, it would have been k power k power k power k power k. Suppose in my reduction I would have said G has an independent set of size k if and only if G has a clique of size at least towers of k, whatever this 1, 2, 3, 4, 5 towers. I mean, really, still now k tilde will become k to the power k to the power k to the power k. Is it an FPT algorithm? Yes, no, maybe, could be, right? So all we need to do is that although the running time allowed is FPT, we need to control the parameter, right? This k tilde parameter must be controlled, right? So instance y k tilde of b such that x is, so now let's rewrite this such that first x comma k is an yes instance if and only if y comma k tilde is a yes instance. Secondly, what we learned, k tilde is at most some function of k, right? Because then it's fine, because then whatever it may be, if it is a function of k, then I can put this, right? If this algorithm would have been for b, would have been running in time tau k n to the power some alpha 2, then my running time of this algorithm will be how much? So if it ran, seed ran, so it would have been h of k plus h of k n times alpha 1 plus tau, suppose this is bounded by some function k, so some function of k times n to the power alpha 2, and this is perfectly fine, right? Okay. But there are more things which we should understand here, okay? Third, time to construct yk tilde could be as much as h of k times n to the power alpha 1, where h is some function of k alone. What else can you say? How much y is bounded by them? K is bounded purely by this, but how much y you can bound? What would happen if y is some will something go wrong if y is h of k to the power n alpha? Like y is very large compared to the parameter, like huge. Size of my instance is also some FPT in the input parameter k. Then what happens? Right? Nothing would happen here. Let's see. Now, what is n? N is this, right? So it will become h of k n to the power alpha 1 to the power alpha 2, which is fine. H of k alpha 2 is still a function of k, and n of alpha 1 into alpha 2, because alpha and alpha 2 are fixed constant, this is still an FPT algorithm. So where do we differ from parameter, where we differ from NP hardness or NP completeness reduction is that A, we're allowed to have much more time, as much time as parameterized complexity allows you to take, because all you are trying to say that if we have such an algorithm, then we can design such an algorithm. लॉगिन संयुक्ता को मैसेज भेज आने के लिए. संयुक्ता को मैसेज भेजाने के no. Why? Okay. So your question is why can't k tilde be log n?
f of k to 1.
So let's say log n, say k log n. Let's just say take k log n, just this much, right? Because it will become something to the power k log n, right? And something to the power k log n, because 2 power log n also is n. So even if I had an algorithm with running time say 2 to the power log 2 to the power say here, if I had an algorithm which ran in time say 2 to the power k tilde, even then we are very bad, right? Because this will become 2 to the power k log n, which is nothing but 2 to the power log n whole power k, which is nothing but n power k, right? But in some circumstances you could, right? Because if I had a very good algorithm, right? For example, if I had an algorithm with running time root k, then maybe yes, right? Because then it will become 2 to the power square root k log n, and 2 to the power square root log n into k, we can bound it by some function f of k plus n. So it will depend, but in general, no. I'll give you a very simple example, right? If I asked you the following question, let's say that I want to solve vertex cover star, okay? Because I'm putting a vertex cover star. Input is g and a number k. Parameter is k, but my question is, does G has a vertex cover of size k times log Vg? Look, my parameter is still k, but you have to, even if the vertex cover has size up to k log n, you have to say me yes. Now you can show using exponential time hypothesis or some such thing that we do not expect an FPT algorithm for such problems. Okay, but I do not want to go into this. But if you notice, if I would have asked you k log Vg, this is fine. This is FPT. Why? Because let's apply it to just normal branching algorithm, right? That will run in time log n times k, which is log n to the power k, which is nothing but k power k plus n, right? So it depends on how you define things, okay? But that's like really going into completely complexity theory, which is not the case for today's lecture. Okay, fine. So these are the properties of the reduction which we would be interested in. Okay. So we will be interested in reduction from a problem to another problem, such that we are allowed certain amount of time. We have to control the parameter. The parameter cannot grow unboundedly as a function of n. It can only grow as a function of the input parameter, right? And that's it. Yes?
I have a doubt.
Please ask.
When you were saying in the reduction, it can be instead of n, we have something like hk n to the power alpha 1. Hk will be the n itself. If we take some another n, and it will be part of the k also, the parameter also. So then what do you mean by FPT in that?
No. N, size of the input could be h of k into poly in n, but the parameter is still function of k.
So yeah, that's what I'm saying. If size of n is also some hk n to the power alpha 1.
Yes.
And my parameter is another hk.
Yes.
Okay. So if I say this is FPT for the problem,
Yes.
what does that mean?
Yes. So let's see what does it mean. Here it means, right? Look. So suppose you had tau k into the power alpha 2 algorithm for B, right? And for algorithm A, x comma k, you outputted me the following property. Here's an instance for B, y comma k tilde, where say y equal to, for example, let's just fix an example, size of y is 2 power k times, it doesn't matter, say n to the power 100. This is what y is, but k tilde is say some k power k, for example, right? Now what do I want to say? That look, even with these set of parameters, I should be able to design an algorithm for A using an algorithm for B. And now let's see if we have such parameters, will we be able to design an algorithm for B? Design an algorithm for A using an algorithm for B? And my point is yes. Suppose this is a running time of my algorithm. So now what is the running time of this? It is tau k power k, which is tau was a function of k alone. So now tau becomes a function of k power k alone, which is still a function of k alone. Now what is this? Say n to the power alpha 2. But now my n is this much, right? So let's look at this. 2 power 2 power 2 power k into n to the power 100 times alpha 2. Now which is equal to tau k power k, right? Now 2 power k times alpha 2 times n times alpha 2 times 100, right? Now I can think of this as one function, some another function, let's call it h, let's call it beta of k times n to the power alpha 1 alpha 2. Isn't this an FPT algorithm in parameter alpha, FPT algorithm for A? Right? I can merge these two functions of k into one function, right? So for example, even if you have instance of size 2 power k dot n and you take a square, it is some 4 power k dot n square, because that alpha 2, this alpha 2 is a fixed constant. It's not something which, even it is not something which depends on k, that n will just grow. N, even when I am saying that y has an FPT size, it means it is still some function of k times polynomial in the input size. Do you still have some question, Viva? Or do you still have confusion? Please ask.
Sir, what I want to say, I mean, I might be confused, but I feel even if B does not have FPT, A will have.
Why?
In the format, what I want to say, even if B does not have FPT, A will have. The reason being where if K is part of N, and then we are defining the FPT in such a way, but it's not FPT, right? Even if it's not an FPT, then our answer will be FPT for it.
No. What?
What I want to say is, suppose B does not have any FPT.
Okay.
Something, okay, so there is an algorithm which runs in time n to the power n into some function of k, and that is only algorithm we know for B.
What is the only algorithm you know? N to the power n dot.
Some function of k.
Okay, so
Function of k.
just say 2 power k,
Yeah.
or say 2 power k, just so that n power n doesn't, and then what's the point of writing n power n? Okay, fine. Yes. Suppose this is the only algorithm we know. Yes.
Sorry. Okay, my confusion is clear.
Okay, because then you see we cannot make any algorithm, right? Because now if I substitute here for value of n, even if n power 100, I'll get n to the power 100 n, and that's not FPT algorithm. But if I had here not n, say 3, it does not matter what is this, like even if you give me 2 power k dot n to the power 3, I mean it is some function of k into poly n. You can still, what do you call, you can divide between some f of k and some poly n. Okay, I mean this is just a way to look at it. Now what we are going to do is we are going to assume a problem to be hard, okay, and we are going to build like some 10 reductions today. Let's see how much we manage to do. So basically what I want to do is to show you some reduction and some reduction strategies. Okay, some very basic ones, and then we will see. Okay, so what we are going to assume for now, so let's remember clique problem. Input is g comma k, parameter is k, and the question is, does G has a clique of size at least k? Okay, and what is our assumption? There is no f of k n to the power c algorithm for clique. For any function f depending on k alone and c being a fixed constant. So that's my assumption, right? So what I want to do, I want to make a, what is it called, complexity zoom around clique, or I want to find problems that are at least as hard as clique. Okay, that are at least as hard as clique means I have to start from clique and give a reduction to the problem of our liking. Okay, so first problem we would like to show is okay. So can you tell me one problem which we already have seen, which is as hard as clique? Yes. So look at independent set. Okay, independent set. So what was the reduction, right? So this is a problem and this is what it is. So you all just now gave me a reduction, said hey, just do G complement comma K. Now we can definitely say that G has a clique of size at least K if and only if G complement has an independent set of size K. Right? Proof is obvious. Here's the graph. If I have a clique here, then in the G complement, since what is the G complement? If there's an edge, like take all the edges which are not present there. So if I look at here, since both endpoints are present, there is no edge here. So this is an independent set. So if I have an X which forms a clique, I have a same X which forms an independent set. And if I have an independent set, then I go back in the complement graph. Since there is no edge between any pair and its complement, I have an edge. So I have shown that independent set is also as hard as clique. I'm not using any terminology. All I'm trying to show is that I want to make a complexity around all the problems that are as hard as clique. Okay, so first problem I have shown you that independent set is hard, right? But now notice, right? I could also start giving reduction from independent set. Why? Because are these reductions transitive? Right? So what I mean by this. So now I would like to say that look, if I need to show, I have shown you the first problem to be as hard as clique. So now I am claiming to you that now actually I can also start giving reduction from independent set to something, and that would imply that our problem is as hard as clique. Why? Let us see. So now what does this mean? Okay, A. So now I have a reduction from clique to independent set, and I don't care about anything else, but here went to K. And now if I had a reduction from independent set to say some problem pi, then I claim that there is also a reduction from clique to this directly. Why? Because I take this instance, and I morph this into this instance, right? Now the point is I started with a k which went to k. In the worst case here it could be some function of k, right? So when I compose this reduction, then k has gone to some f of k and everything just remains the same, right? And how will I argue? Oh, this is an S instance of clique if and only if this is an S instance of pi. How? Say, well, this is an S instance of clique if and only if this is an S instance of independent set, if and only if this is an S instance of pi, and that's it. So prove for yourself that FP reduction, which I defined before, is transitive. Okay, so now what I would like to show, that which is a very important and good starting point for lots of reduction, is clique in regular graphs. So what I would like to show now is that regular clique. Input a graph G, number K, where every vertex in G has same degree, right? In other words, G is a regular graph. Okay, parameter is still K, and the question is same. Does G has a clique of size at least K? Oh God.
You can't see the area of the board where you're writing.
Oh, you can't see?
No. You're out of the.
Is this okay?
No.
This?
So it on this third column.
Or you can't see anything in the third column?
The camera is not on you. Okay.
Now can you see? Now can you see the third word?
Yes.
Fine. Okay, so now we have to show that, look, all I am saying that we still want to have a clique, but when I start with clique, I have no guarantee that every G is a regular graph, every vertex has same degree, but I would like to reduce clique to a regular clique. Okay, what I would like to do, I want to reduce clique to regular clique. So what should I do? I have a G comma K and I want to in this, and it's a polynomial time reduction. It's not that we are going to take non-polynomial time. So how do we reduce this? So all we have to do is to start from an instance of graph and obtain another instance G star for the clique where every vertex in G star has same degree. Okay, is the goal clear? Okay, any idea? Yes, that we have to do. We have to add extra vertices. You're right, but in a particular way. Which way? let D be the maximum degree of G. Okay, fine. That's what he said. And let di, okay, and let dg of V denote the degree of a vertex in G. Okay, fine. I have fixed this notation so that we can talk in this language.
So this vertices which has degree dv of g is less than d. We add d minus dv of g extra
Pendant vertices. Fine.
Now we have to fix the degree for this pendant vertices.
Because now they are singletons, like they have degree 1. So here is your smart trick. You can call it smart trick. Not something which I have discovered, but I mean the world knows. So what you do is a very amazing, beautiful trick. So now let's see if I can use it. So what you do, you make this is G1, G2, GD, right? So basically Gi is isomorphic to G. So basically take D copy of G. What is this? It is a D copy of G. Okay. Now here's a clever trick which you do. You look, I mean, if you try to pick a vertex here and try to make pendant, then you will land up into the same trouble as C landed up into. So what you do, you have, so every vertex V, let's fix a vertex V, every vertex V has a copy in each, right? Let's call it V11, V12, V1D. So every vertex has one copy each in this. Now what I'm going to do, I'm going to make a new vertex set V1, V2 and VD corresponding to every vertex. And how many vertex a Vi will have? It will have D minus degree of G of Vi vertices, and this is an independent set. What is this? This is an independent set. So next property, take D copies of this. Second, each Vi is an independent set containing how many vertex? Containing D minus degree of G times Vi vertices. That's it. Now, what? Right. Yeah, you're right. Vn. Now what you do? Take a Vi copy and make him adjacent to every Vi copy in each. So for example, V1, I will make him, every vertex here is going to be adjacent to this. This guy is going to be adjacent to everybody, right? So what is the next thing? Next thing is, okay, let's make every vertex in Vi adjacent to Vi1, Vi2, Vid, right? Basically make every vertex in Vi adjacent to every of its copy. Okay, claim 1. This is the construction of G star. Okay, this completes the construction of G star. G star, and what is K star? Is K. K star is K. claim 1. Every vertex in G star has degree D. Right? Why? Because look at any vertex, right? So it has some degree and it gets remaining degree from its Vith copy. So every vertex here clearly has same. Now look at any vertex here, right? This guy has neighbors to all its copies in every graph. So it's by definition has degree exactly equal to D, right? So every vertex in G star has degree D, right? Look at a vertex here. He has some local, how many neighbors? D, G, V, I, and the remaining D minus D, G, V, I he gets from here because these guys are adjacent exactly to those vertices, right? And this vertex has degree D because every vertex is one guy each in each graph, and there are D such graph. Okay, so this is claim 1. Claim, so this is fine. Claim 2, if G has k-sized clique, then so does G star. And this is trivial. If G has a clique, then G has a clique in some, look, each graph Gi is a copy of G. So just go to any copy and you will get a this clique in that copy because each Gi is isomorphic to G. So I will in fact have the same, like I will have clique into the K all in all the D copies of the graph. So just go into one and you are happy. Okay. Proof, just project to a copy of G. Claim 3, if G star has a clique of size greater than or equal to K, then so does J. Now let's ask ourselves, can a clique be part of this thing? Two copies of Gi? No. So every clique is completely contained inside this, and maybe something from here that I am not denying. All I am trying to tell you that every clique is completely contained inside Gi and maybe some Vi vertices. But now let's look at some Vi vertices. Okay. Now first of all, my claim is no vertex in Vi, claim no vertex in Vi is part of some triangle. No vertex in Vi is part of some triangle. Why? Because look at any vertex in Vi or on here. This vertex has edge exactly one neighbor in each copy, right? So if how can it be even part of the triangle? To be a part of triangle, look, this guy, it has just one copy here. This guy has just one guy. So basically when I look from the V and its neighbors, they are one each into this. And to make a triangle, it must see two vertices in the same copy of G because it's an independent set here. So if we would have started our assumption, but K could be a part of two size clique, so we can assume K where K greater than or equal to 2. Right? Now, sorry, 3. No, because K equal to 1, 2, it's anyway FPT, like just check, right?
If K is equal to 1, then the graph itself is regular because it's an independent.
No, even for the proof, right? K equal to 1 and 2, we shouldn't care. The problem is FPT. It's actually polynomial time solvable. So is part of the clique, is no part of the. So if K is greater than or equal to 3, what does it mean? None of these vertices can participate into clique, because if a vertex participates into a clique, it also participates into a triangle, right? So each vertex here does not even participate into triangle. So what do you talk about being clique? It means this implies if G star has a clique, then it is in some Gi which is isomorphic to G, and we are done. Okay. Any questions, or did you understand the reduction? Yes? No? What? Degree of this guy? Okay, what is its degree here? Is GV1, right? Okay. What is its degree here? It's DGV1. And what was D? D was a max degree. So what is D minus DG bear? Say 10. Then he has 10 neighbors here, right? Which one? This guy? No. Yes, every vertex here gives neighbor to its, like every vertex here gives a neighbor to its copy. That's why I have n vertex set, right? For each Vi in G, I have a vertex set, which has exactly how many neighbors, how many vertices? D minus degree of G times Vi, so that it only supplies to these vertices. So this guy only takes care of the copies of Vi in every component. This guy takes care of copy of V2 in each of these guys. That's it. So it's like a supply demand question where this guy only supplies to these people. Okay, fine. Okay, okay. So now what I would like to do is another clique question, and let me see how much color coding all of you people know. Okay, fine. Okay, so now I can forget this. Okay, what I want to show to you people is what is called multicolor clique. So another version of clique which is very useful is called multicolor clique. Okay, input is G comma K, okay, or no, input is G being partitioned into V1 to Vk, okay, V being partitioned into V1 to Vk, and E and a number K. Okay, question is, does G has a K size clique C such that C intersection Vi is equal to 1 for all I from 1 to K, right? So basically I can think of my graph as being partitioned into V1, V2, Vk, and what I am asking for, is there a clique containing exactly one vertex from each partition? So for without loss engineering, I could have also assumed that this is independent set, because all I am interested in clique which consists of this. Okay, any reduction? So I would like to have a reduction from clique to multicolor clique. This is, let's call it MCQ. This is CQ clique. I do not want to keep writing. Okay, so let's write this part. Okay, so what I want to do, again it's a polynomial time reduction actually, right? And the way things are set up, I mean, any idea from there? Why this TV goes away? Any idea? Yes, no, maybe, could be? What did you people learn last class? What did you learn in last class? Yeah, but what was the last class? What was the subtopic which you learned?
The color coding and de-randomizing.
Ah, yeah, wait. Color coding. Okay. So what was the property of what did you do for color coding? For which problem? Wait. So on what?
The multicolor path of this.
Exactly. So what happens if we apply that reduction here? Apply that like the first part of that if we apply here, what happens? What did you apply for the first thing for the K path?
Randomly commute the colors.
No, after what was the last algorithm? Randomly. There was also you also got C power K, E power 2e to the power K algorithm. Am I right? So what did you do for the getting 2e to the power K algorithm?
Randomly color the vertices and then find
Randomly color the vertices from what was the range of colors? From 1 to 1 to
1 to k.
great. Okay, let's just do that. Okay. So given an instance G comma K, randomly color the vertices of Vg from 1 to K. Okay. What is the probability? What is the probability that if G has a K size clique, say C, then C has become colorful yes. So does it depend on the size? Exactly. Right? So the probability is K factorial divided by K power K, which is like roughly 1 over E power K. Now, what do I do? As a reduction, I can output this random partition, right? This randomly colored. So all the vertex which has been colored 1, I make it V1. All the colors which are all the vertices which have been colored 2, I make them V2, and all the vertices which have been colored K, I make them Vk. Now, if G has a K size clique, then with probability 1 over E power K, I have a K size clique here, which is, so this is my multicolored instance, right? And if I have a K size clique here, it's nothing but the same graph, so of course I have a K size clique here. So this is a randomized reduction, so now since I need to boost it to get, I don't even need to boost it because this is an FPT reduction, right? I can take and look, I can, to be sure that this is a correct instance, maybe I can repeat it several times. But this is a valid randomized reduction, right? It's a valid FPT reduction, randomized reduction, because which succeeds with, which creates an instance of multicolor clique with probability 1 over E power K, right? So this is my instance, right? So I did nothing, I just uniformly at random colored the vertices, right, from 1 to K, and I got K partitions of the vertex set. And what is the property? That if G had a K size clique, then definitely it has a K size clique with probability 1 over E power K, right? So forward direction happens with 1 over E power K probability, and if reverse direction, it happens with probability 1. Right? If this has a K size clique, then it's the same graph, right? Right? If this has a K size multicolor clique, then it is the same graph. So I have this. But this is not, so this is what I'm trying to tell you, that you have at times in FPT reduction much more freedom which can be exploited, right? But as I promised you, I would like to have a normal reduction, not this fancy reduction. This is a very fancy reduction, which you need at times when you are not able to make non-fancy ones. Okay, so let's now make a non-fancy reduction, like normal polynomial time many one reduction from here to here. And I basically have told you how to do it. What I do is, okay, I think we will use it here. Okay. Okay. So what I do is very simple. You will see it's really not very hard. Okay. So what I do is that suppose I have G comma K with say vertex set of G V1 to Vn. Okay. I make K copy, let's call it W1 to WK or YW V1 to VK. Okay. And here I have V11, V1, no, what am I writing? Say V11, V21, Vn1, and here we will have what? V1k, V and k. And each Vi is an independent set. What is this? Each Vi is an independent set. Now, how do I give an edge? It's very simple. If there is an edge between Vi and Vj, if there is an edge between Vi and Vj, then give an edge between Vi alpha, Vi say A, Vj B, A not equal to B, right? That's it. And what is, where is A comma B? Is in 1 to K, right? So basically, if 1 comma 2 was an edge, right? Then I give an edge from where? First copy of this to the second copy here, first copy of this to second copy in another one, another one, another one, another one, another one. So basically this, between every pair, if you look at, between every pair, you look at every color class Vi and Vj, you look at, you basically have an edge between this vertex and this vertex. If you look at the, project yourself back in the original graph, there is an edge between those two vertices, and that's it. Okay, now my claim is same. So this is my construction and this is my partition, my construction, and this is my partition. So let's call this G star K. So what I would like to show first, suppose G has a K size clique. Say Vi1, Vik, right? Just go, I mean, what is it? Go Vi1, 1, go Vi2, 2, go Vik, K. I claim to you this is a clique in my this graph. Why? Because, well, if there is an edge between them, how did I put an edge between them? If the corresponding pair had an edge in the original graph, then between every pair I had made an edge. So clearly I have an edge between these two guys. Right? Okay. These are simple reduction, they are not hard. I mean, there's no fun. Did you get it? No? No? So you should ask, no? How did we give an edge? Okay? So let's look at a 3 vertex graph. Okay? Let's call it V1, V2, V3. Okay? And suppose we had 2 partitions. Okay? So look at this, what I did. I said V1 1, V2 1, V3 1. So this is the first copy of the same vertex set. Now there is a second copy of this vertex set, right? I mean V2 1, let's say, let's make it even third copy so that we can capture this triangle. V2 1, sorry, V1 2, V2 2, V2 V3 2, V1 3, V2 3, V3 3. Now what did I say? If there is an edge between V1 and V2, then look at the fix a pair. So now let's just fix a pair V1 and V2, and I say, oh, V1 and V3 has an edge. So look at the 1th copy here and the 3rd copy here. Let's put an edge between them. So I put an edge between them. Okay. Now what is an edge between, say, 2 and 3? Also there is an edge, right? So look at the 2th copy here and the 3rd copy here. I make an edge. Okay. Now, okay, fine. Now I have never said A less than equal to B or B less than equal to A, right? Look, so now look at, so we have put this edge this way. Now look at 2 1. So 2 1, look at the 2nd copy here and look at the 1th copy here. I put an edge. Now look, but if I look at the same edge from the 2th perspective, there is also an edge from V2 to V1 and V2 to V3, right? So I also put an edge between this, right? So for every pair in A not equal to B, right? A not equal to B, right? If the corresponding guy has an edge where A comma B is from 1 to K, I never said that A is less than equal to B. I mean, there could be anything, right? So basically, what will this correspond to? It will correspond to complete bipartite graph here. Similarly, between any two pair, it will be complete bipartite graph here. So now let's look at V22 has an edge between V3 and V1 in this part. So he goes here, but he will not give an edge to himself, right? So what we should add here? I not equal to 0, right? But since I was only talking about edge Vi and Vj, by definition they were different. But just to make sure that we don't get confused, I is not equal to j, right? So basically, only edges which you are not giving here is between identical copy. Right? So this is how you give your edges. So now what has happened? If you look between these two guys, if you look from this side, it's an edges of your original graph. You look from this side, it's an edges of the original graph. Right? Now if I have a 3 vertex, look at 3 vertex here. So I look at V1's copy here and V2 copy here, they are distinct vertices. Agreed? V3 copy here, here. Now by definition, when I look, there is an edge between them because there is an edge between 1 and 2. Okay. Now when I look between 2 and 3 here, there is an edge between them because there is an edge between 2 and 3 because there is an edge here. So there will be an edge here. Now when I look back between 1 and 3 here, because this is what I am marking here, they also have an edge between them because, oh sorry, here there will be an edge like this, right? So that's where the triangle I am talking about, right? So basically what I am doing is between every pair I am maintaining the edge relationship of my original graph. I am just trying to preserve the edge relationship of the original graph, okay? And the reverse direction, what we will say? Well, if I have a multicolor clique, then I have a multicolor clique how? Some vertex from here, some vertex from here and some vertex from here. Say I have a V1 1, V1 2 2, V1 K K. These are my clique in G star. And I want to claim that go back and look at Vi1, Vi2, Vik. They form a clique in your original graph. Why? If not, suppose there is a pair of vertex which does not have an edge, look at that, look at the corresponding copy, how are they forming a clique there? Because I have given an edge between every pair and every not equal to j, and that's it. So if you think for a minute for yourself, this reduction is not very hard, okay, fine. But remember the trick with color coding, that's a very useful trick to have. Because you can de-randomize also, right, using hash functions. So you will get a Turing reduction we get a Turing reduction, which means that we cannot have an FPT, and that's perfectly fine for many purposes. Because for many purposes, we may not be able to make such a reduction. There are some, at least I know concrete examples where this is the only way I know forward. Okay, we'll see in the DOM set reduction for FPT approximation. That's the only way I know. Okay, good. So now for the today, I'll give you the last reduction today. Okay, last. Yes.
Sir, I wanted to ask why we are okay with the randomized reduction in the case of FPT, and while we are doing reduction for NP completeness, generally we don't go for. I haven't seen randomized reduction.
We do, but we do not. Then we cannot say no. When we make a randomized reduction, we cannot say that it cannot have a deterministic polynomial time algorithm. When we make a randomized this thing, we can only say about certain thing cannot happen, right? So when I give this randomized reduction, which I did to you some time back, right? What will it imply? It just implies that with certain probability, right? Like clique cannot have a randomized algorithm. We do not expect clique to have a randomized FPT algorithm, right? That's all that it says. It never says that clique. No, what does it say?
Multicolor, assuming that clique does not have.
Exactly. All it says that this problem, multicolor clique, does not have an FPT algorithm if clique does not have even randomized FPT algorithm. That's all that it says, right? So in the classical setting of parameterized complexity, it means nothing. It will not. It only says that for this problem we do not expect to have certain kind of algorithm, right? So we are making a much more stronger assumption. What is the stronger assumption? That clique does not even have a randomized FPT algorithm, because then only I can conclude that this problem does not have an FPT algorithm. Now when you do an NP hardness reduction, yes, you can make a randomized reduction, but then you will rule out certain randomized polynomial time. Like what will you say? Oh, SAT, if SAT, so if we assume that SAT cannot even have a randomized polynomial time algorithm, then this problem is NP hard, right? So for example, okay, so look at a paper from 2000 something, I don't remember, of Mojes Charikar, which shows that feedback arc set in tournament is NP complete, which was open for a long time, and the first reduction was randomized reduction to show that this problem, assuming that NP does not have a randomized polynomial time algorithm, this problem is NP hard, and it was later de-randomized. So even in classical NP hardness we do show sometimes, but it is not that often. And even in FPT world, we do not show most of the time randomized reduction. We show normal reduction, but at times it is convenient to show randomized reduction. And as I said before, right, this will not imply a many to one reduction, but I can make it a deterministic Turing reduction. How? Rather than using this coloring, I can use hash function. So what will I do? I will create not one instance, but I will create some e power k into poly n many instances of multicolor clique, such that if the initial graph had a k clique, if and only if one of these instances has a multicolor clique, right? So, and this is a complete perfectly deterministic Turing reduction, right? And what does it imply? I cannot say W1 hard in this. All I can say that multicolor clique does not have an FPT algorithm unless FPT is equal to W1, because what I have done is given you a Turing reduction, meaning I have created that many reduction, that many instances of multicolor clique starting from clique, that if you solve any one of these instances, if you solve all these instances, then from one instance at least we will be able to get an yes answer. And if for all of these they do not have a multicolor clique, it means the original graph does not have a multicolor clique, because we know that at least in one instance these vertices of clique have been properly colored, and that's it. Is that clear? No? Yes? I will send you the paper where they do show such reductions even in polynomial time world. Should we go ahead? very painful teaching this. Okay, maybe. Okay, here's a homework.
We can get there are k factorial distinct multicolor cliques in G star.
Yes. Yeah. It will blow up to many of them. You're right. If there is one, then there will be k factorial.
If one is there,
Then there will be k factorial.
corresponding to that we can get a k factorial.
Yes, I agree, completely agree. So 1 has become k factorial, if it has 0, it is 0. Maybe it's a useful thing to have. Okay, yeah, it is useful for counting too. You show lots of gap. Okay, fine. So let me just tell you one problem which is obvious, but still my job is to tell you, and we will see the reduction next time, but at least let me tell you the problem at least. It's called partial vertex cover. Okay, what is this called? Partial vertex input is G, K and S. Parameter is K, and the question is, does G has a set C subset of VG, cardinality of C at most K, and the number of edges, and it has at least S edges incident to it. Okay. So if I put S equal to E of G, then what is this problem? This is same as vertex cover. But when S is not, I do not want to cover all the edges, but I want to cover certain number. I tell you how many edges I want to cover, right? And I give you a budget of K, right? So this is called partial vertex cover problem. And here are those people who are smart and interested. Okay. Okay. So this problem does not have a polynomial kernel. This problem does not have a polynomial. Sorry, this problem is W1 hard, which we will show next time. But this problem is known to be okay. This is called partial vertex cover. It is known to be partial vertex cover is FPT on planar graphs, bipartite graphs, at least I know this much. Okay. Also, okay. And the question is, do they admit a polynomial kernel? Kernel, compression. Okay, it's an open problem. It's not a homework problem, please. And if you ask for lossy kernel, yes, they do. Yes, they do. So someone needs a research problem, so we will show W1 hardness, and here's a research problem. I don't think it's too hard or easy, this I don't know, but here's a problem. Okay, so we'll meet next Monday and we will do more reduction. So I will take 2 more classes and I will do maybe 15 to 16 more reductions in W1 hardness. That's the goal. Okay.